Hello, everyone. My name is Zachary Stever. I'm a PhD candidate in operations research at the University of Buffalo, and today I'll be talking about the classification and relation of mixed integer linear programs using graph convolutional neural networks. So I'd like to begin today's talk by posing a simple question: what is a mixed integer linear program? I think the easiest explanation is that these are mathematical models of system dynamics. So as an example, on the left, we have the MILP, or mixed integer linear programming, formulation for the bin packing problem. This is a problem that most of us are familiar with. You need to pack a fixed number of items into a number of bins, and you'd like to minimize the number of bins required to complete this task. But it turns out that this same formulation has been used to model problems such as task allocation among employees, investment in capital projects, and processor scheduling in parallel computing, among others. And so we see that problems or systems which may appear to be unrelated may actually share a similar, or in this case, identical mathematical structure when modeled as MILPs. And so the focus of this research is in identifying a way to classify and relate MILP formulations so that we may uncover relationships between different problems. When we talk about relating MILPs, we typically look at MILP instances, or realizations of an MILP formulation. For example, on the left, we have an instance of that bin packing formulation we saw on the previous slide. In 2019, Gleixner et al. Introduced a method for measuring the similarity between two instances. They do this by defining feature vectors, which include 100 manually defined instance statistics, such as the mean right-hand side value among constraints. They then take the Euclidean distance between two feature vectors and use that as a measure of the similarity between the corresponding MILP instances. Our group at the University of Buffalo also introduced a methodology which uses images. These images capture variable activity in constraints, and then using a convolutional neural network, feature vectors are automatically extracted from these images, and again, Euclidean distance is used as a measure of the similarity between the corresponding instances. The issue with these approaches is that neither representation is exact. That is, given a feature vector from either approach, you could not reconstruct the instance that it represents exactly. And so we introduce in this work a new surrogate representation for MILPs, which is an exact representation for an instance, and we use this representation to learn MILP structure and classify MILP instances. And this representation we refer to as MILP graphs. So this is actually the graph which exactly captures the bin packing instance we saw on the previous slide. But before we get into how we construct this graph, we need to cover the concept of instance primitives. So we contend that any MILP instance can be exactly defined given these 8 instance primitives, which we say are the attributes which are both necessary and sufficient to define an MILP instance exactly. They are the objective function sense, maximization or minimization. For a variable, the variable type, lower bound, upper bound, and objective function coefficient. For a variable and constraint pair, the coefficient of that variable in that constraint. And for a constraint, the constraint sense, less than or equal to, or greater than or equal to, and the right-hand side value. So let's show how we construct an MILP graph for a given instance. First, we create a node in our graph for every variable in our MILP instance. Next, we create a variable for every constraint. So this is constraint 1 or C1, this is constraint 2 or C2, etc. Next, we draw an edge between every pair of active variable and constraint. So x11 is active in constraint 1, so there's an edge there, but x11 is not active in constraint 2, so we do not draw this edge. Next, we set the constraint coefficient primitive as the edge weight. So in constraint 1, it's 1 x11, so this receives an edge weight of 1. In constraint 3, it's 2 x11, so this edge receives a weight of 2. And finally, every node receives a 6-element node feature vector. These node feature vectors capture 6 additional instance primitives. In order, they are the variable type, lower bound, upper bound, and objective function coefficient, These will obviously be zero valued for constraint nodes, followed by the constraint sense and right-hand side value, which will be zero valued for variable nodes. Of course, we need numeric values in these feature vectors, so we introduce numeric indicators for both variable type and constraint sense. And finally, the 8th instance primitive, which has not yet been discussed, is objective function sense, minimization or maximization. So we capture this indirectly. We assume minimization for every MILP graph. And if an instance was actually maximization originally, we simply multiply every objective function coefficient value by -1. It turns out that when you do this for instances of many different MILP problem types, we see many unique graph structures appear. Obviously here we've left out the feature vectors for clarity, but it's clear that many unique structures appear. And so what we want to do is train a neural network to learn these graph structures and then be able to classify or predict which problem type that graph structure is associated with. And we do this using a graph convolutional neural network, or GCN, which is pictured here as a black box. Unfortunately, we don't have a lot of time to open the black box in this presentation, but as a high-level overview, graph convolutional neural networks were introduced in 2016 by Kipth and Welling. They extend traditional convolutional neural networks by operating on graph-structured input data. They typically include two primary components. These are tensor mapping, mapping one tensor to another, which is just how a traditional neural network operates. And then they include what's called a message passing paradigm, where nodes share their feature vectors with neighboring nodes. And this helps convolve the graph and give us a sense of local graph topology. And the task of taking input graph structures and outputting class probabilities, or in this case, problem type probabilities, is referred to as graph topology classification. And this task is well documented in the literature with GCNs. So in order to train a GCN, we first needed a training set of data. So we went to the Structured Integer Programming Library, or StripLib for short, and we collected instances from this site for 19 unique problem types, which are listed here. So we see our bin packing problem here, among many other well-known problem types. Our training set, includes 40 instances for each of these 19 problem types, for a total of 760 instances. And we generated the MILP graphs for each of these instances. I won't spend a lot of time on this slide, but the training procedure took 3 hours and 23 minutes. It included 100 training epochs, and the convergence of our training loss is shown over here. I should note that our graphs were constructed using the Deep Graph library, and our machine learning platform was built on PyTorch. Next, we tested our trained GCN on a test set. Our test set included 10 instances for each of the 19 problem types. These instances were also taken from the StripLib, but were not included in our training set. For classification accuracy, we treated the class with the highest probability for any instance as the predicted class. So here we see that all 10 of our test bin packing problem instances were predicted to be bin packing problem instances. In general, we see a relatively high classification accuracy across all 19 problem classes. We can also look at the average probability of belonging to the correct class. So the average probability that a capacitated vehicle routing problem instance belonged to the capacitated vehicle routing class was 99.8% for test instances. And across our 19 classes, we see in general, many of these classes have near 100% probabilities of belonging to the correct class. Now, we do see for several of these problem classes that the probabilities are a bit lower. For example, our bin packing problem instances receive on average a 75% probability of having come from the bin packing problem. But this is actually explained if we look at the top two class probabilities. So Again, those bin packing test instances had a 75% probability of coming from the bin packing problem. But the next highest class probability was that they came from the bin packing problem with item fragmentation. And so if we combine the probabilities of belonging to these two classes, then we find that there is a 99.3% chance that our bin packing test instances come from either the bin packing problem or the bin packing problem with item fragmentation. We see a similar trend here with the scheduling problem. These instances had on average a 60% probability of coming from the scheduling problem, which is still a correct prediction, greater than 50% chance. But the second highest class is the relaxed click class. And so the test instances from the scheduling problem had a combined 92% probability of coming from either the scheduling problem or the relaxed click problem. Now, the relationship between these two problems is less intuitive than between bin packing and bin packing with item fragmentation. But when we look at the graph structures for these two problems, we start to see that perhaps there is something similar between the structure of these two formulations. And so this is the case where we would go and inspect the relationship between these two problems. Additional results which are worth mentioning are scalability. So our graphs scale well with instance size. To examine this property, we generated a new formulation for a new problem. This is not one of the 19 problems from the strip lab. This is the generalized lot sizing and scheduling problem. And one of the key model parameters for this problem is the number of products. And we see as you increase that parameter value and we get increasingly large instances, we see a similar structure at varying densities. So this was a 3-product instance, this was a 9-product instance. And so we generated 20 different sized instances of this problem, 3-product, 6-product, 9-product, all the way up to 60-product instances. And we find that across these varying sized and density instances, we always recover a high probability of these instances coming from the lot sizing problem, which is good because this was a generalization of the lot sizing problem. And we see that this value does not change very much as these instances scale. So of these 20 instances, the lowest probability of belonging to the lot sizing class was 99.5%, and the highest probability among these instances of belonging to the lot sizing class was 99.74%. So we see that our approach scales well with instance size. Additionally, we have this property called graph isomorphism. And what graph isomorphism means is that no matter the order in which you define the nodes and the edges, you will always recover the same graph structure, just twisted about itself or rotated about itself in some way. And in our case, variables and constraints are represented as nodes and edges. So this means that when we define the same instance in any order, we will always recover one common graph structure. And so to test this, we coded another new problem. This is the product recovery and remanufacturing problem. This problem is also reminiscent of the lot sizing problem. So secondarily, we wanted to see if this would be classified as a lot sizing problem. We generated one instance of this problem, but generated it in 20 different random permutations. So just different orders of when we define the variables and constraints. We find that all 20 permutations yield one common identical graph structure, which can be verified by this graph isomorphic property that we have. And furthermore, no matter what the permutation was, we always received the same probability, 99.84% chance that this problem is related to the lot sizing problem. And so we're also able to relate this new problem, product recovery and remanufacturing, to this traditional lot sizing problem in the literature. And so in conclusion, we find that MILPs may share similar mathematical structure even if they're modeling unrelated problems. We introduce a graph-based representation for MILPs that is exact, it's interpretable, it's scalable, and it's isomorphic. And then through machine learning, these graph structures can be used to classify and relate MILPs totally agnostic to the MILP's application area. So thank you very much. I hope you enjoyed this talk, and thank you for taking the time to listen.